Alright guys, section 4.4 part 2. We're going to go through some of the homework problems, talk about how to interpret some of the problems. A lot of terminology today is what we're going to focus on. How to read a problem, how to know what the problem's asking you, and then how to apply the different theorems and values from the problems we've talked about so far into more of a word problem setting. You can see the homework assignment listed here. I will also post it onto the classroom itself. We're looking primarily at the second half of section 4.4, which is on page 318 in the PDF or on page 294 in the textbook. Now, I'm going to do a lot of the even ones, primarily because I want you to get the extra practice from the odds. That's why I assigned them. I will be answering questions about those on Saturday for anybody that has them, and we'll use that time in order to understand better just what we need to do. So I'm going to start off by doing number 58. Okay. The graph shows the velocity in feet per second of a decelerating car after the driver applies the brakes. Use the graph to estimate how far the car travels before it comes to a stop. If you're reading this picture, it doesn't look like it tells you what you need to know. It doesn't give us a distance in any form. In this particular picture, it tells us we have time on the x-axis, and we have velocity. There's nothing about distance on here, which is why it's important for number 58 to remember a certain relationship. Way back in chapter 2, we discussed how a derivative allows us to take something like distance, use a derivative to find velocity. We then talked about how you could use a derivative with velocity to determine how to find acceleration. And if this isn't ringing a bell, perhaps the next one will. We used it one more time to find something called the jerk. And that's not just me. Got it. So we can use derivatives. If we have the distance formula, we can use a derivative to find the velocity formula. If we have the velocity formula, we can use a derivative to find the acceleration formula. If we know the acceleration formula, we can use the derivative to find the jerk formula. But now that we've connected this chapter, we know that if we integrate, it performs the opposite function. So going down this list, we use derivatives. If we wish to go up this list, well, that's not even close. If we go up this list, we have to integrate. Now, if we look at this picture, we also know that integration is, by definition, the area under a curve. It's always true that this is the case, which means that if I have the jerk formula, the area under that curve will tell me the acceleration. If I have the acceleration formula, the area under that curve will tell me the velocity. If I have the velocity formula, the area under that curve will tell me the distance. And so this relationship is very important to understanding number 58. So how do we do number 58? And by respect, number 57? Well, we need to find the area under this curve. They do not come out and say this, because they shouldn't have to. In this example, you should be able to look at a problem, read what this says, and go, say, velocity. Oh, we want to find distance? We need to integrate. Or if we don't have a formula, we need to just manually find the area under this curve. So for this problem, I'm going to estimate just by using a very standard technique, counting the squares. Now, this is a little bit harder because the graph is not a nice graph, but I'm going to do my best here. To do so, I'm going to count out how many squares we have. I'm then going to multiply that by how big each square is. This is an old-fashioned technique you can use. I happen to like it. It helps reduce mistakes, because if I just count the squares, those squares could have various meanings. Each square could be 1 foot, or it could be 20 feet. It's impossible to tell, and so that's why we're going to take this step. If you look at this picture, a way I know this is going to give me the right answer is because if I do this, the number of squares is a number. However, the size of each square is found by taking length times width. The length in this case is the feet per second. The width in this case is a time, which is in seconds. If you know your basic calculations, those are going to cancel and give me back to feet, which is pretty nice. So I'm going to find the number of squares in total and how big each square is, multiply those two numbers, have my answer, and make sure it makes sense. So Let's take a look. How many squares are we looking at here? Well, let's take care of the easy ones. 1, 2, 3, 4, 5, 6, 7 full ones. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 full ones. We've got really close to another full one right there, so I'm going to call that 23. Another really close to the full one right there, 24. We have a half square and another half square. You can see how these kind of have matching pieces. I make that 25, 26, 27, 28. I'd say maybe 28 and a half, maybe even 29 would be pretty dang close as the number of squares. And if you feel that you count differently, it's always possible. I'm working on a computer screen. Maybe your textbook is better. Just, if that is the case, use the group chat, help each other out. Okay? Now, next you need to know how big each square is. Well, if you look down here, you can see that each square is half a second wide and 10 feet per second long. So we have half a second. So this is my time. This is my velocity. And you should know from physics, velocity times time will always give a distance. This tells me how big each individual square is. This tells me how many squares there are. I multiply those two results, I get my answer. So I get 28 and a half, or close to it, times half times 10 would be 5, and 28 and a half times 5 would be 142.5. I know we're supposed to get a distance. I see in my problem I have feet, so I go with 142.5 feet. That's it. Notice the process we have to take in here. We have to first understand the underlying concept. That's what's big about word problems. They do not give you the formula. You have to understand the formula. Next, once we understand the formula, we have to take the next step, which is, okay, I have distance, or I have velocity, I want to find distance. So I have to integrate, or I have to find the area under the curve, whichever is appropriate. If they give me a picture, area under the curve is a good bet. If they don't give me a picture, they give me a formula instead, probably going to integrate instead. Now, from there, we have to then sit there and say, okay, if I'm finding the area under the curve, how do I do that? Conceptually, we'll have to find out how big each square is, and then find out how many squares we have. Each square is 5 feet, so if there's 28 and a half squares, it must be close to 142.5 feet. And again, this might be a little bit off because of how we counted the squares, but I would guess an appropriate range would be between 140 and maybe 150, depending on how you count your squares. This is my range of expectation. You're always going to have this whenever you're looking at a graph like this because you're not going to have exact numbers. And so, in this case, I would accept an answer in between here. As long as you can justify it, that was an answer I would accept. Okay, let's talk about one like 59 and 60 are really close, but they are very different. And so doing number 60 doesn't really help much with 59. So I'm instead going to go to number 62. Okay. The velocity v of the flow of blood at a distance r from the central axis of an artery of radius r is this. Ooh, that's a lot of words. Let's keep going. Where k is the constant of proportionality, find the average rate of flow of blood along the radius of the artery. Use 0 and r as the limits of integration. Ooh. Okay, so we're supposed to find the average rate of flow of blood. Okay, so this tells me we're trying to find an average, which tells me immediately I need to look to one of my theorems. There is a very strict theorem that's supposed to tell me the average rate of flow. If I go back up to my book, let's see, particle motion, that's not right. Net change, it didn't ask me how much it changed, it asked me what the flow's average was. And if I look right here, I see average value, that's looking good. Yes, here we go. This is where we're going to find the average value of the function. So we want to find the average rate of change, this is what I need to use. So I immediately go here to using this formula. 1 over b minus a integral from a to b of f of x dx. Okay, I've got the hard part down. I know what formula I'm supposed to use. Now we get to the theory part. I have to know how to plug into this formula and what to plug into this formula. Notice that they've given me a couple of extra hints here. So first of all, they've told me V is equal to K big R squared minus little r squared. Okay. First, they told me in the problem that K is called the constant of proportionality, which means K is constant. It's not a variable, it is a constant, which means that when we integrate, it will integrate like 5 or 3. And 3 times anything is not going to change the integration process. Next thing they tell me is that r, distance r from the central axis, or radius r. So again, capital R, in this case, is supposed to be a constant. Or at least it's going to act like one, which is really important. Okay? Because in this case, little r is the only real variable at play. So when we integrate, we're going to integrate with respect to r. You have to know what you're integrating with respect to in order to do this problem. Am I integrating with respect to K, big R, or little r? Those are the 3 possible options. And if I don't know that question and how to answer it, then I can't do this problem. So now I can just start plugging stuff in. 1 over, okay, B and A are supposed to be the starting and ending places, or what we call the limits of integration. Notice that below the problem it says use 0 and r as the limits of integration. So I use 0 and r as my 2 limits of integration. You might ask, well, which one do I put first? It turns out it will not matter for this problem. It literally will not matter, because whatever happens to this problem will be fixed when you do it over here, because these are opposite statements. Next, I plug in the formula, which is K big R squared minus little r squared. And I'm taking the derivative with respect to the only variable in question, which is r. Doctor. Okay. So I've got my function. This is supposed to tell me what the average rate of change is supposed to be. Now let's start simplifying some stuff. Let's get to the actual meat of this problem. Okay. 1 over r minus 0, well, that's just 1 over r. K is a constant, which means that I can actually bring this constant out, meaning it doesn't do anything. So I can actually take that K and bring it outside the integration. Left with a now simpler version, big R squared minus little r squared, dr. Let's make sure we know those steps. I took this function, r minus 0 is r. The K is a constant, which means I can bring it outside according to one of my properties of integration. Okay, now, next piece. This r, the big R, is a number. It is considered constant. Little r is considered to be the variable. So now that I can take the step, I'm going to integrate. Okay, we have K over r out front. And now I'm going to integrate this function. R squared, big R squared I should say, is a number. It's like 12 squared. It's a number. So when I integrate a number, I end up with the number times the variable. That's a big step to make. We haven't talked about that very much. So let's talk about it a moment now. When you have a number, like say this problem wasn't r squared, let's say it was 3 squared. 3 squared would become 9. And when we integrate 9 separated by addition and subtraction, it would become 9r, because remember, this has a power of 0 on it when it comes to the variable. So when we integrate it, we add 1 to the power like normal, and then divide by the new power, which is why r squared becomes r squared little r, because r squared is a number. And so when we integrate it, it acts like any other number. It becomes the number times the variable. Minus, add 1 to the power, divide by the new power. So that'd be r cubed, divide by the new power, that'd be 1/3. Evaluated from 0 to r. Okay? So far, let's follow our steps. Original problem had k over r, k over r. R squared becomes r squared little r, because again, r squared is a number. A number, when you integrate it, becomes the number times the variable. Minus, r squared becomes r cubed divided by the new power, which is 1/3, or 1/3 r cubed. And we are still integrating from 0 to r. All right. There's a lot of variables floating around here, but I bet a bunch of these are going to disappear here shortly. So let's take our steps. Let's plug in big R and followed by little r. This is our fundamental theorem of algebra, which states that when I integrate this function, it will become capital F of b minus capital F of a. Don't forget the number up front, k over r, times. All right, we plug in r. This becomes r squared times r. Everywhere there used to be a little r, we plug in big R. Minus 1/3 big R cubed. Okay, minus. Okay, so this is our f of b. Minus our f of a. Everywhere there used to be a little r, now goes to 0. So we have r squared times 0 minus 1/3 0 cubed. Now how about that? This last piece, because everything is times 0, is going to go away. Which means I'm left with just this first piece, which is k over r times, okay, r squared times r is r cubed, minus r cubed times 1/3 is 1/3 r cubed. Now these are the same number with a 1/3 in front, so I do k over r times, if I have 1 r cubed minus 1/3 r cubed, I would have 2/3 of an r cubed left. I now distribute. The r on bottom is going to cancel with one of the r's on top, leaving us with r squared. The 2/3 and the k are constants, giving us this answer. 2/3 little k r squared. It's a little harder to do math when everything's in terms of a variable, so have some respect for the people who do physics. If you want to talk about a fun mathematical process, physics is awesome. It's stuff like this all the time. It's the best. Do it. It's great. Okay. Real physics anyways, not the high school crap. Sorry, coach. So we get 2/3 k r squared. This is, in this case, the average rate of flow of blood along the radius of the artery. So closer to the wall, this will be different. Closer to the center, it will be different. But the average, 2/3 k r squared. That's pretty cool. So we were able to successfully do an entire problem with 0 real numbers. I mean, you have 0, but 0 kind of does its own thing. I never think of it as a regular number. So look at that. That's awesome. And that's number 62. It's very, very similar to number 61 and very similar to number 63. So note how we did it. And let's take a look now at number 64. Oh, by the way, when you're doing this problem by yourself, I've shown a lot of extra work just to make sure I follow all of my steps. If I'm being completely honest, I would probably jump straight from here to here. Because, well, plugging it in is not the hard part. I can take the derivative and plug in at the same time. But it's up to you how much paper this is going to use. If you do find yourself running out of paper, do make sure you have enough. Okay. 64. Average sales. The company fits a model to the monthly sales data for a seasonal product. The model is blah, blah, blah. Lots of stuff. Okay. Where S is sales in thousands, as T is time in months. So we're dealing with a function in terms of T. A. Use a graphing utility to graph the function. That's not hard. Use a graph to explain why the average of f of t is 0 over the interval. I'm guessing if that's the case, it probably indicates that this graph, it's a sine graph, so I know what a sine graph looks like. I'm guessing it does one of these. We have an equal number of positive values as you do negative values, thus why the average would be 0. B. Using a graphing utility to graph s of t and the line g of t equals t over 4 plus 1/8. In the same viewing window, use the graph and the result of part A to explain why G is called the trend line. Okay, so remember from algebra, the idea of a trend line is that it should match the flow of the function over time. Now, if you have a collection of data points, they're never going to be a perfect linear progression. If you do, like, it's actually one of the things you can look for to determine if a company is cheating on their taxes. If they have a nice, straight, linear amount of data, like this just doesn't happen in the real world. It never has. Data's nasty. Data's wild, okay? You will have, if you look at the stocks of a company, they will do all kinds of crazy stuff. And you'll be like, hey, predict what's going to happen next. You're like, don't know. It's very rare to see a nice, smooth progression like this. And companies and the IRS use information like this to say, I'm not going to do that. That's bad. So the trend line in this case indicates that this is supposed to be what's average happening over time. Okay. I would bet that for this problem, since it's entirely all about graphing, the main focus should be to understand how to put these functions into a graph and to interpret the results. We've done both. So 64, boom. I didn't even need a picture. Look at that. All right. 66, the capstone. I actually assigned that one before we went on break. Before I do anything else, let's take a look at the next problem we have. We have 67, 69, and let's go ahead and do two of those. So let's look at 68. Okay, 68. In the exercise 67 through 72, find f as a function of x and evaluate it at x equals 2, x equals 5, and x equals 8. Okay, so 68. First part, find f as a function of x. This is possible through the second fundamental theorem of calculus. The second fundamental theorem of calculus states, if I have f of x, so this is the second fundamental theorem of calculus. If I have f of x equal to an integral from a to x of f of t dt equals f of x. So in other words, did I write that right? I already wrote f of x. So in other words, I can simplify this function and it will get back to f of x. Make sure I get that from the book. Scrolling. So much scrolling. Yes, there we go. So, the second fundamental theorem of calculus states that, in other words, the derivative of these two gets us back to f of x. There we go. Cool. Maybe you don't need a second fundamental theorem of calculus. Interesting. At first glance, it looked like a second fundamental theorem of calculus question, but I don't think it is. Okay. So I'm going to drop that. All right. Let's now look at 68 with fresh eyes. F of x is equal to the integral from 2 to x of t cubed plus 2t minus 2 dt. All right. First, I'm going to actually solve this integral, which means I'm going to start by integrating the function. T cubed becomes 1/4 t to the 4th. Remember, we add 1 to the power, divide by the new power. 2t becomes t squared, divided by the new power. 2 divided by 2 is going to be 1, so I'm going to just leave that. Minus the constant becomes 2t, evaluated from 2 to x. Okay, let's plug in. Remember, when this happens, I now need to plug in the top number first, then subtract plugging in the bottom number. So we do 1/4 x to the 4th plus x squared minus 2x minus 1/4 times 2 to the 4th plus 2 squared minus 2 times 2. Everywhere there used to be a t, I replace with x. Everywhere there used to be a t, I replace with 2. Let's simplify. So I have, the first piece is pretty much consistent. 1/4 x to the 4th plus x squared minus 2x. All right, what happens with this piece? 1/4 times 2 to the 4th. 2 to the 4th should be 16. 1/4 that should be 4. 4 plus 4 minus 4, a lot of 4s. The 4 and negative 4 are going to cancel, leaving a 4, but there is a subtraction in between those. So this becomes minus 4. This answers the first piece, which says find f as a function of x. Done. Then it says to evaluate when x equals 2, when x equals 5, and when x equals 8. Well, evaluate just means plug in. So the first piece is I'm going to plug in 2. 1/4 times 2 to the 4th plus 2 squared minus 2 times 2 minus 4. As it turns out, through some creative magic, I already know the answer is 0. That is because, if you'll notice, this number is a 2. If I put a 2 in for x, that would mean that these two have the same number, and according to one of our theorems of calculus, that means that the end result will always be 0. It's actually a property from section 2. Okay, x equals 5. I would do 1/4, and you can verify that result by actually solving that. We would do the 5 to the 4th power plus 5 squared minus 2 times 5 minus 4. This one I do not know right off the top of my head, so I'm going to do it. 5 to the 4th is 625 divided by 4. Better check that result. $150. $6.5. I was off by 10. Ooh, that hurts. All right. Plus 5 squared is 25. Minus 2 times 5 is 10. Minus 4. Okay, so these two, this become minus 14. 25 minus 14 is 11. And 156.5 plus 11 will be 167.5. Always check my results, please. If I probably made a mistake, it was right there. All right, 8. So again, everywhere there used to be an x, I replace with an 8. 1/4, 8 to the 4th, plus 8 squared minus 2 times 8 minus 4. Okay, go down here. 8 to the 4th power. So that'd be 64 times 64. That's a big number. I'm going to simplify some of that. So it'd be 64 times 8. $512. Plus 64. Minus 16. Minus 4. Okay. 16 and 4 will be minus 20. That becomes 44. 512 plus 44 will be 556. Nice round number. Ooh, I hope that's right. 556. Oops. My box. Okay. There it is. All right. And the other ones are very, very similar. The only difference between this one and the next ones are that you might have something like, oh, you have to convert this into a different form in order to take this integration, because you can't do 20 over v squared, but you can do 20v to the negative 2 power, and then you got to trick one down here for extra practice. Okay, let's now go to like 75, these ones. Okay, let's see if I can use this space over here. So we also have 75 through 89. Let's answer a couple of these. Okay, 75 through 89 states, integrate to find f as a function of x. Demonstrate the second fundamental theorem of calculus by differentiating the result in part A. Oh, so basically check your results. Do I get the same function when I integrate? Okay, so we did 75 through 75 through 89. I'm going to do 76 as an example, showcasing what I'm looking for. It says f of x is equal to, we have the integral from 0 to x. Remember, the bottom number can be anything, but the top number had better be x. it says we have t times t squared plus 1 dt. Well, let's integrate this. Before I can integrate this, I'm going to simplify some. I don't like this being multiplied because you have a variable times something, and those aren't easy to integrate because they're not in our standard list. But I can if I distribute. This becomes t cubed plus t dt. That's much easier to integrate. Okay, this will become 1/4 t to the 4th plus 1/2 t squared, evaluate between 0 and x. I can then plug in x and 0. This would become 1/4 x to the 4th plus 1/2 x squared. And I plug in 0 into the same thing. I can already tell that this plugging in 0 is going to cause it to disappear. That's okay. I'm going to go ahead and show my steps though. So plus 1/2 0 squared, which will leave me with 1/4 x to the 4th plus 1/2 x squared. Now this is part A. How do I do part B? Part B just says, well, show the second fundamental theorem by differentiating. So I'm going to take this 1/4 x to the 4th plus 1/2 x squared and take the derivative. Notice I have to take the derivative with the new variable because that's what variable is happening in the problem. I can't take it with t because t is gone. When I differentiate, I get this new function. Well, I would multiply by the power. The 4 times the 1/4 are going to cancel, which means that I would then subtract 1 from the power, leaving me with x to the 3rd. I then do the second part, plus 2 times 1/2 would give me just 1, so that fraction disappears. Subtract 1 from the power, it would become just x. And there's nothing else to differentiate, so I'm done. You'll notice that this is the exact same as the original, just with x. And that was the whole point. That's the second fundamental theorem of calculus, is that if I differentiate an integral, they essentially cancel each other out. But you can do it by creating a new variable, which is pretty cool. Okay. For 81 through 85, let's go ahead and take a look at those. All right. Let's look at 82. It says specifically to use the second fundamental theorem of calculus to find f prime. Okay, so in this case, I can predict what the answer is going to be. I will hide it just for a second on the other side of the page. Kaboom. You ready for this? Easiest problem in the world. Okay. All right, I got my prediction. I hope you didn't see that. Let's do this. So it says f of x is equal to this integral, which is 1 to x of x squared plus 1 dt. Oh, damn it. I didn't say anything. Equals, and to go from 1 to x of t squared over t squared plus 1 dt. Now, this problem does not fit into any of our standard forms, and I cannot rewrite it. There is no way to rewrite 82 into a form that can be solved. Now, if we have our book, we can actually look and see there are other versions that we can change. This is one of them. I believe this is a hyperbolic function. But the way it is right now is simply impossible. So we have to actually understand the meat of this question. And the meat of this question is, I want to find f prime. What am I given? Well, I currently have f. How do I get f prime? I take f and perform a derivative. But if I got to do that to one side, I have to make sure to do it to the other. So this is how I get to f prime. And at this point, I can now take the shortcut. I know that this is the second fundamental theorem of calculus. This entire right-hand side is just a second fundamental theorem of calculus. which means that I know that the result of this function is going to be the original function, t squared over 2t plus 1, replaced with x. So notice how I used f to find f prime by using the theorem to cancel out the integral. But when I cancel the integral, I have to do it to the new variable, not the old variable. And kaboom. Easy. All right. So there's 82. And 84 and 86, these are actually very fast problems once you realize what they're asking for. The people who don't realize it will spend a lot of time trying to do them. I'm sorry. Get good, scrub. Okay. Exercises 87 through 92. You notice it's the exact same thing. They just didn't tell you to use the second fundamental theorem. I suggest you do. You can also use some properties to help fix this, okay? You can use properties to help fix this. If you don't know how to use the second fundamental theorem, then I suggest you just do the integral and then afterwards take the derivative. There are properties that can help fix some of them if you're willing to use them. If you are not, just go through the steps. Okay, let's look at the last couple. 97, 99, and 101. So, in the exercises, the velocity function in feet per second is given for a particle moving along a straight line. Part A, find A, the displacement. Part B, find the total distance that the particle travels over the given interval. At this point, let's have a short mini lesson. If you are not in physics, you may be confused. What the heck is displacement and how is it different than distance? Okay, let's talk about a box. This box has sides that are each 1 unit long. Yay. And on this box, there is a little bitty ant. Look at my beautiful ant. He looks so happy. You can't see it, but he's smiling. Okay, if this ant was to travel along the box, sticking to the edge of the box, never leaving, never going up or down or anything crazy, just traveling along the edge of this box, you would say he has traveled a total of 4 feet. But this is actually the distance. As it turns out, he has actually traveled 0 feet if you talk about something called displacement. Displacement is the distance from the original starting point. Now, it's important to note that distance and displacement are related. If you take the displacement and do an absolute value of it, you will find the distance. This is a natural process because displacement can be negative. If I, for example, take another, instead of a flea or an ant, let's just take a line with a little dude on it. If he travels forwards, let's say 3 feet, you would say he has traveled a distance of 3 feet, and if you stop, you would say he has a displacement of 3 feet. In this case, distance and displacement are the same. But if he travels from there and comes back, in total, he would have traveled a distance of 6 feet. However, his displacement would be 0 feet because he ended up right back where he started. That is because, according to displacement, going away counts as a positive value. Coming towards would count as a negative value. And so in this case, they have canceled each other out. If you did an absolute value as you were going, though, the negative would disappear and become positive, meaning you would get back to the 6 feet. This is a little mini lesson for understanding displacement because you cannot do a particle problem unless you understand what it means when it says find distance versus finding displacement. As it turns out, an integral, just a standard integral of velocity, will always tell you the displacement. So if I integrate with respect to the velocity function, it will tell me displacement. As long as I tell it where to start and where to stop. This is always the case. If I just integrate the velocity function, it will tell me the displacement. Because remember, when you look at the graph of that function, you can have pieces that are above and below, meaning you have positive areas and negative areas. Well, if I do a very similar one with an absolute value, this will tell me the distance. It is listed in your book this way. It's the last thing before the homework, which means it is right there we go. On page 292. It shows an example of this. It's a great example. Please take a look at it if you are ever confused about this, because you'll notice that when it talks about displacement, it gets one answer of 32 over 3, which is a little less than 11. When it talks about distance, it got a larger answer, an answer of almost 12. 71 over 6 is almost 12. And so it's different answers because in the picture, you can see that there is a part above the graph and a part below the graph. Well, when you do a basic integral, it's going to take this part as positive and the other part as negative. When I do the absolute valued version of the integral, it's going to take them both as positive and put them together. So there's your little mini lesson. Make sure, if you haven't noticed, this one is a big one. I told you before, this is on every single AP exam. Every single one. I have never, ever in all my years seen a single AP exam that didn't have one of these questions on it. And it's one of those that if you know what you're doing, you either integrate with respect to the function or you integrate with respect to the absolute value. That's it. But if you don't know what you're doing, it makes this real fun, real fast. Okay. With that in mind, let's now look at one like 98. As you can imagine, based upon what I just said, we're going to do two problems. Part A is going to do this version, which is going to give me displacement. Part B is going to use the other version, which is going to give me distance. The only difference between them, the absolute value symbols. So let's take a look at number 98. It tells me V of t is equal to t squared minus t minus 12. And the time we're looking at is from 1 to 5. Let's talk about part A. Part A, we're going to integrate from 1 to 5 the velocity function t squared minus t minus 12 dt. For part B, I'm going to go ahead and write it out because I know it's going to happen. From 1 to 5, the absolute value of t squared minus t minus 12 dt. And we'll talk about how to fix that after part A. Okay, part A. So I've got the function. Let's integrate. This will become 1/3 t cubed minus 1/2 t squared minus 12 t, evaluated from 1 to 5. Your basic integration, very helpful here. Okay, now let's do the two components. Plugging in 5, 1/3 5 cubed minus 1/2 5 squared minus 12 times 5. The first part minus the second part when I plug in 1. When I plug in 1, it becomes 1/3 times 1 cubed minus 1/2 times 1 minus 12 times 1. Okay, let's solve this thing. Okay, 5 cubed is 125, divided that by 3 is 125 over 3, minus 5 squared is 25, divide that by 2, that'd be 25 over 2. Notice I'm not simplifying yet, I'm going to save that to the end. 12 times 5 is 60. That's the first piece. Now I'm going to simplify up here first, and then do the subtraction afterwards. 1 cubed is 1 times 1/3 is 1/3. 1 times 1/2 is 1/2. And 12 times 1 is 12. Now, I do the negative. So minus 1/3 plus 1/2 plus 12. And from here, I simplify. 125/3 minus 1/3 becomes 124/3, which I believe will simplify. Give me a second. Maybe not. Negative 25/2 plus 1/2 would become negative 24/2, which is going to simplify. Negative 60 and positive 12 is become negative 48. Okay. Next piece. All right. 24/2 is actually minus 12. And negative 12 and negative 48 becomes negative 60. Oh, hey, those canceled. That would have been convenient. Okay. All right, now let's put this over 3. So, negative 24/3. This would become negative 180/3. Faster than that room. And negative 124 minus negative 180 would become negative 54. Sorry, negative 56/3. Okay. So what does this tell me? Well, if we think about the picture describes a particle moving along a line. So here's a particle, and here's the line. Displacement tells me where does it fit with where the start was. So if we started here, this tells me that my displacement is in the negatives. So we ended up somewhere over here. So we started here and ended here. Because where I started, my displacement is negative. That means it has to be backwards of where I would normally want to go. So if I start here, this is my displacement over there. But it's possible this particle started by moving this direction and then slingshotted backwards. And in fact, that's exactly what's going to happen here, is that in this example, it started off backwards and slung back. It could have started and gone forwards and come back. It could have gone and gone farther backwards and slung back in this direction. We don't know. Displacement doesn't tell you a whole lot. And so it's important to understand both components in order to fix this problem. So that's why we do part B. Now, to do part B, the easiest way by far to do this problem is to have a picture, because it can tell me exactly where this function is going to change, where it's going to have this absolute value actually matter. Because remember, an absolute value takes negative values and makes them positive. Well, it turns out, through some experimentation, I actually know where this is going to happen. This should happen at positive 4. Yep. So, by rewriting this function, we go from 1 to 4, and from 4 to 5. How do you get that without being magical? Well, it's actually pretty easy. You take this number inside and set it equal to 0 and solve this equation. When you do, and I use the quadratic formula to do that. You can also factor it, which is perfectly acceptable. You get negative 3 and positive 4 as your two answers. However, only one of those is in between our two boundaries. In this case, 4. So 4 is where this function changes from either positive to negative or from negative to positive. Now the question is, which one does which? They're both going to have t squareds minus t minus 12. But because the absolute value, one of these is going to change. Instead of being positive, it's going to become negative. Instead of being negative, it's going to become positive. Some of these is going to change. It turns out it's the first one. This is a big, 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 big detail. And it helps if you know what this graph looks like. I know, because of how much I've done these kinds of problems, that this graph looks a little something like this. And so I know it starts negative and becomes positive later. Because remember, we're going from 1 to 4. So I know it starts negative, which means this one is the one that has to be fixed. And the second one is the one that's just fine the way it is. It takes practice to get this piece. It helps if you have a picture. If you look back at the example in the text, again, I cannot stress how useful this example is. Look at this example. It talks here about how you can find that piece and determine which ones need to be broken apart and how to determine which ones are broken apart. Right here. It's so helpful. Please use it. Okay? Again, it is on page 292 at the very bottom. If you are having any troubles with between 97, 99, and 101, look at this example. Page 292 in the book. Okay, let's finish this now. So, I got my two components. Let me go ahead and take my time and find out each of those. Now, this first one, I'm going to plug in 1 and 4 into that problem. And then the second one, I'm going to plug in 4 and 5. Now, for this first one, I plug in 4, and can use the information I have up here to simplify this process a little bit, because I already know what the integration is going to look like. This will become negative 1/3 t cubed plus 1/2 t squared plus 12 t from 1 to 4 plus 1/3 t cubed minus 1/2 t squared minus 12t from 4 to 5. Okay, getting some extra space here. All right, boom. Okay, so for this problem, let's now find these two components. Equals. Okay, I plug in 4, get an answer, plug in 1, get an answer. That's the first piece. So I start by plugging in 4. Negative 1/3 times 4 cubed. As you can imagine, part B is significantly longer because you have to make a few choices, which is really the big defining factor here. Okay, and then plus 12 times 4 minus, okay, now we plug in the 1, so you negative 1/3 times 1 cubed plus 1/2 times 1 squared plus 12 times 1. Okay, so that's the first one, plus the second one. So plug in 5 and 4. Okay, plug in 5. 1/3 times 5 cubed plus, minus 1/2 5 squared minus 12 times 5 minus, that is the same thing with 4. Okay, so we do 1/3 times 4 cubed minus 1/2 times 4 squared minus 12 times 4. Okay, all that's left is just simplifying this nastiness. Okay, again, the first one comes from solving that first integral, the second one from the second integral. This will find the total value, which should be different than that negative 56/3 that we found earlier from part A. Okay, whew. Let's do each part. All right. 4 to the third power would be 64 times negative 1/3. That would be negative 64/3. Plus 4 squared is 16 times 1/2. That'd be 16/2. I could simplify, but I'm going to just take care of all that at the end. Okay, 12 times 4, that would be 48. So plus 48. All right, minus. So 1/3 times 1, this will become negative 1/3. Okay, distribute the negative sign. So double negative would make this positive. Distribute the negative next one, just make this minus. 1/2 times 1 is minus 1/2. Distribute the next one. 12 times 1 is minus 12. That's the top line. Plus, the same thing with the bottom line. 5 times 1, I actually did that before, didn't I? Yeah, okay. So this would be 125/3 minus 25/2 minus 60. Okay, so the first piece. distribute the negative, so distribute here, distribute here, distribute here. So become minus, okay, 4 times the third power, that's 64. Oh, hey, you might notice that this one is going to match. These two are actually end up being the same. It's actually pretty common. And sometimes one of these in the middle will cancel, which is even better. But use what you can to help you out here. Okay, let's take our hair pieces at a time, Okay, we have negative 64 over 3, another negative 64 over 3. That becomes negative 128 over 3. We have a positive 1 over 3 and a positive 125 over 3. Okay, 128 plus 1, that become 127, 125. This becomes negative 2/3. Whew, all those put together. All right. So that takes care of this one, and this one, and this one. Okay. All right, next one. Let's do the halves. So we have 16 over 2 minus a half minus 25 halves plus another 16 over 2. Okay, so there's all the 16 over 2s. All right, 16 over 2. That becomes 32 over 2 minus a half. That becomes 31 minus 25. That becomes 6 over 2. Double check. Yep. All right, last one. We got 48, 12, 60, and 48. Okay. So 48 and 48 is 96. Minus 60 becomes 36. Minus 12, that becomes plus 24. Oh my gosh, look at this. This comes fun. All right. 6 over 2 is 3. 3 and 24 is 27. So we have 27 minus 2/3. Okay, this becomes 81 over 3 minus 2/3, which is, for a grand total of 79 over 3. Look at this. First of all, note, it is a positive number, and it should be. Distance is positive. Geometry is right there. Distance should always be positive. What this tells me is my displacement, you remember, was negative 56 over 3. But my total amount traveled was 79 over 3. So even just looking at those two, they're different values. This one tells me I ended up to the left, negative 56 over 3. This tells me I traveled a total of 79 over 3. So I must have either started off here and gone a little bit to the right and slung back, or I must have started here, gone too far, and brought it back to here. One of those two things has to happen. And it turns out what happened was this function started here, it slunk back, and came back to here, traveling a total of 79 over 3 units. As you can see, the first piece, straightforward, relatively simple. Second piece, a lot harder. So again, use page 292 as an example. It's called example 10. Use it, abuse it, do what is necessary. Use this piece to help you out with the last couple of problems. Page 292, example 10. That'll about finish it for me. With that information, you should be able to solve the rest of the problems. Tomorrow, we'll be taking a look at the next section. Just get started on it and see what we can do. And let me know what you think. I'll talk to you guys tomorrow.